All right, so these are going to be our notes on heat and energy notes. So if you haven't opened your classroom, go ahead and start. It's on heat, Q, and fusion vaporization notes. I'll tell you what those are. But here's my slides, and then here's the Cornell notes. You're going to make sure that you're going to highlight at the end and write a 3 to 5 sentence summary for me. And then you're going to link a completed notes onto page 70 of your notebook. All right, so let's go ahead and get started. All right, so heat and energy. So our essential question for these notes is, what is heat capacity and how to use it? Okay, so we're going to talk about what heat capacity means, and we're going to talk about it for a good week or more before we actually get to our exam, okay? All right, so a couple definitions I kind of want to give you is heat, or Q, and / energy, mean those are the same thing. Energy that transfers from one object to another, and it always flows from warmer to colder, just like the ice that was in your hand, as the energy flowed from your hand to the ice to cause it to melt. Temperature is very different. Remember, it's the measurement of kinetic energy in substance, so how fast something is moving, about movements, okay? And then we have specific heat or heat capacity, which we'll talk about those. How much heat or energy it takes to raise the temperature of a substance 1 degree Celsius. So it depends on mass, and we'll see how this all works together, okay? So specific heat capacity, let's start off with that one a little bit, okay? And it is the amount of heat, calorie or joules, we are going to work here in just joules, needed to make 1 gram of a substance go up 1 degree Celsius, okay? And different substances have different specific heats. And we'll play with those in class. We'll look at, again, ice melting and putting on different surfaces and which one melted first and why. And so which has a higher specific heat and so forth, okay? A low specific heat capacity, C, and it's just a letter, and you'll see the equation in a minute, means a substance heats up fast. So it's kind of like blacktop or metal, right? If I put it out in the sun, that stuff's going to heat up super fast. And then high specific heat capacity means a substance heats up slow. It takes more energy to get it there. So something like plastic. So if I put a piece of metal and a piece of plastic outside in the middle of summer, 115, the metal's going to get a whole lot hotter faster than the plastic. And that's because it takes less energy, okay, to get the metal to heat up, okay? So it takes less joules to heat up a metal. It takes more joules or energy to heat up a plastic, okay? We'll practice with this a couple times. So this is our equation. You do have this on your equation sheet. This is all you're going to calculate. You're not going to have to calculate MC or what delta T is. You're just going to need to know how to identify different things to calculate Q, or how much energy, okay? So this is kind of split up, but here we go. These are the units, and this is how when I go through some of these practice problems, and I'll show you, just like in the gas lab, I use the units to identify what they are. So energy can either be in units of calories, cal, or joules. This is mass in grams. This is specific heat, which I'll show you what those are. Basically, these are easier to identify, and then you know what specific heat is. And then this is a triangle, and it means delta. It's a Greek letter. It just means change. So change in temperature. And I will usually say delta T. And it is in Celsius, okay? Not like in gases as in Kelvin. This, because we're not just in gases, we're in all kinds of substances, then we go ahead and use Celsius. So C, our specific heat capacity. You will not have to calculate this. This is something that scientists have done hundreds, millions of times. And so each substance out in the world has a calculated average specific heat capacity. So it will be given to you, or you look it up in a table. And then, of course, M is mass in grams, okay? Delta T, or change in temperature, okay? And we always do final minus initial, okay? So this is something you're going to have to identify to calculate Q, or heat, is you're going to have to identify what is the final temperature. That means what does it end up at, and then minus what it begins at, okay? So this is a specific heat table. I wanted you to see this, okay? So these are different specific heat capacities of all kinds of substances. So things that have a high specific heat, things that take a lot of energy to heat up, such as things like water, okay? Ice, steam, of course, they're all part of water, and glass, okay? So those take a lot of energy, and you can see the highest is water. So you can think about, yeah, that's why my pool in my backyard doesn't heat up as fast, right? It takes a week of really warm temperatures to get it to heat up on its own, okay? And kJ is just kilojoules, okay? Still joules is just kilo in front of it, okay? And then we have, again, some low specific heat capacities, which means they heat up super, super fast, okay? Which means there's mercury, which is why we used it in temperature in measuring temperature in thermometers, okay? Steel, if you put steel out, gets hot super fast, and aluminum, okay? And some other high ones would be hydrogen takes a lot of energy to heat up, and so does wood. And that's why a lot of the play structures you see are made of wood, because they don't get hot to the touch as if I made one out of steel, which would be like, whoo, ow, no one wants to get on those slides, right? In 115-degree weather when it's a metal slide. No one's getting on that, okay? All right, so we're gonna look at a couple practice problems. You'll do more in class with me, but here's our equation, Q equals mass times specific heat times delta T, or change in temperature. So here is a question, okay? So calculate the amount of energy in joules required to heat 145 grams, so this tells me that's a mass, of water from 22.3 to 75. Well, remember I told you you're gonna have to identify the final temperature and the initial. So it's from, so this is where I start, this is where I end. So this one, first one would be our initial, and this would be our final, okay? So the first thing we're gonna do is calculate delta T, or change in temperature. And it's gonna be final, 75 minus 22.3 will equal 52.7, okay? Then I will start putting in the numbers. Remember, C is going to be from the table we just saw. So it says water, so we're gonna go back, we're gonna look at where would I get that? So you would have water, and you could see there's 3 different ones. So depending on what they asked you to calculate in kilojoules, kilocalories, or calories, you would use one of these. And I believe we've used here in this one 4.186. So it is one that is given to you, okay? So then we just kind of put in our numbers. Well, Q equals the mass is 145 times 4.18 times 52.7, and it would get you 31,900 joules, okay? And this 4.18 is not kilojoules, it's in joules, okay? All right. There's a cup, so that's how you would work heat. Okay, but there's 2 very specific heat calculations that we're going to learn about in here. And one is called the heat of fusion. And remember on our phase change graph, that heat of fusion, I told you, was where we go from an ice to a liquid or liquid to ice, okay? So this one right here, let's look at it. It is the energy used to melt or freeze a substance already at the melting point. So it's just like water. This is how much heat or energy it takes to either take a liquid to 0 degrees Celsius or ice to 0 degrees Celsius, okay? So formula, there's no temperature change, because remember when we're going through a phase change, temperature doesn't change, right? So this equation gets a little simplified for us. The first thing, we don't even need a specific heat because we have tables that have heat of fusion of all the substance. People have calculated those for us. So we have Q, or energy, equals heat of fusion from a table times its mass, which is in grams. So you will only have to calculate what Q is, okay? The other one that we'll also work with Q is called the heat of vaporization. And heat of vaporization is a point like at water where we're at 100 degrees Celsius, right? Where we're either going from right there between the liquid, we're boiling to go to gas, or we're condensing to go back down to liquid. So either way, so this is that 100 degrees Celsius point. And this is the energy used to boil or condense a substance already at the boiling point or condensation point. And this equation, again, remember in a phase change, there's no temperature change, so we got to throw that out. And all these equations are on your equation sheet in your notebook. So Q equals heat of vaporization times mass. And again, you will calculate Q. You will be given the heat of vaporization in a table and the grams. The biggest point on the exams is that you're going to have to identify, do I need to use the heat of fusion or the heat of vaporization? And that tells you, reading through to determine what phase change I'm in, okay? So let's look at a sample problem. So we're going to do the heat of fusion, and it says here, calculate the amount of energy in joules required to freeze. So right there it tells me that has to be the heat of fusion because that's going from a liquid to a solid, okay? 145 grams of water. The heat of fusion of water we would always give you is 334 joules per gram. So then we just go ahead and plug in our numbers. So Q is going to equal heat of fusion, 334, times 145 grams to get you 48,400 joules. So the biggest hurdle to jump over these problems or to determine, am I going to use the heat of fusion or the heat of vaporization? Okay, let's look at another one. So now we're going to use heat of vaporization. So how much energy must be removed to condense? So again, that tells you between a liquid and a gas, condense. So you do have to learn those vocabulary words. 146.7 grams of water vapor into a liquid. So I will start plugging in my numbers, okay? The heat of vaporization of water, which you would be given, is 2,260 joules per gram times the mass, 146.7 grams. And if you multiplied it out, you would get 331,500 joules, okay? All right, so what I want you to do is go back and highlight important information, make connections with your notes, write any questions in the left column, and then write a 3 to 5 sentence summary of your notes. We are going to practice the heat calculations sometimes in class, so make sure you're understanding when do I use heat of fusion, when do I use heat of vaporization. If you have any questions, please get a hold of me.